Hello and welcome to our physical sciences session. My name is Temba Nube. Today we are focusing our attention on the physics part, which is your paper one. For the sake of interaction, we are having our WhatsApp line. You're more than welcome to make any contributions. It could be questions, clarities, it could be comments on any matter that relates to today's point of discussion. The WhatsApp number is 064 748 8913. I'll repeat the number once again. Is 064 748 8913. Now, the purpose of the WhatsApp interaction is to get you actively involved in the session, by making contributions and also seeking clarity. It can be used also as part of our discussion, just to get a sense of whether we are moving together or there are some challenges. But then it's only for text messages. Be reminded that you must not send, your voice notes, your videos, and whatnot. So the purpose of the WhatsApp group is to specifically, get us discussing on the matters that relate to today's topic. Right. Now that we've gotten that out of the way, Gretos, our focus for today is on the mechanics, which is, a total of 65 marks. But what exactly are we zooming our attention into for the purpose of today's session is work, energy, and power. It's in paper one, it is the physics, the mechanics as the knowledge area. Now, without any waste of time, let's look into what is it that we want to actually achieve by the end of today's session, right? Okay, by today, we need, the end of session, we need to be able to, remember, keep key definitions of the concepts involved in work, energy, and power. And once again, Cretos, be reminded that when it comes to definition, it's all or nothing. So by the end, you must be able to recall definitions. But what's so important about definition, besides being an all or nothing type of a situation, is that you need to capture the keywords in the definition in the correct order, and they must be used in the correct context, which explains why when it comes to recall or remembering skills, you are either given full marks or zero, right? So we need to recognize that work is done on an object by a constant force. So in other words, what are we saying? We need to understand by the end of today's discussion that what does work on an object is actually a constant force that acts on that object. Okay, now that we've mentioned force, and remember, the entire mechanics as a knowledge area is centered around the concept of the force, right? That's where it all begins, right? Now, for us to say a particular force does work on an object, okay, we need to be able to correctly identify those forces. And this comes in many, ways. It could be your force diagram, it could be, your free body diagram, something that we already know about, okay? Right. And then routine calculations from 3 marks upwards. And remember, whenever a question has got a 3-mark allocation, what that simply says to you is that it's a straightforward routine calculations. Draw your attention to the data sheet, okay? Identify the correct formula, do the necessary conversions if there's a need for that, and then subsequently carry out the calculation by use of a scientific calculator and make sure that the settings are correct, okay? Because there's often a challenge when it comes to the use of the scientific calculator. And remember, the final mark is for the correct magnitude, including the unit. If it's a vector, direction has to be also taken into account, right? So the word net is something that comes quite often in our discussions. When we talk about a net, we're talking about a total. So we'll do a number of calculations around determining the magnitude of the net force or network done on an object, okay? And beyond that, it was also important, we need to be able to tell the differences. If there are similarities, well, we'll also look into that between a force doing positive work on an object and a force that does negative work on an object, while we also pay careful attention to forces that do not do any work. And I think it's also important to mention this now, that for us to be able to identify forces doing positive work, we need to understand the big question in as far as when does a force do work on an object. Okay, we shall delve into the detail of that discussion. And then the work energy theorem, what we'll find very interesting today, is the integration of what we already know, from grade 10 and 11 when it comes to vectors, in two dimension, when it comes to forces in as far as the Newton's laws. There'll be something very interesting there to discover at the end of this session. Right. Applications of the work energy theorem comes from the fundamental understanding of what the theorem is all about and where it comes from. Now, with that understanding that when a net force acts on an object, what happens to the object, in terms of the Newton's second laws, we'd see a very, very strong, attachment between the work energy theorem as far as the Newton's laws, particularly the first and the second law, right? So those are the objectives. Now let's get into the bolts and nuts now. Okay, when is work done on an object? These are some of the very critical questions that one needs to ask themselves. Okay, when is work done on an object? There must be a constant force that acts on the object. Let's call that force F for argument's sake. Okay, it must act on the object, and then what must happen to the object as a consequence or as a result of that force, constant force acting on the object? The object must be displaced. Okay, and immediately, if you talk of displacement, what exactly comes to mind? It talks about the change of position. Now, as a result of a force, a constant force F acting on an object of a given mass, then that object changes its position. Then work has been done on that object. But we need to be careful of the fact that what actually does work is the force. There are a number of forces that act on an object while the object changes its position or while the object is displaced. Now, the critical question is, which of those forces or force does work on the object? Now, the mathematical equation or formula for determining work is capital letter W, is the product of force and displacement. Okay, and then the cosine of theta is actually the angle between those two vectors. Work in principle is a scalar quantity because it is a result of a product between two vectors. Which vectors are we talking about? We're talking about the constant force F as well as the displacement of that object, which happens in a specific direction. And by now, we want to think of it in terms of linear motion or motion in one dimension. Hence, there will be a specific direction of change of position. Okay? Now, so we are clear with the angle theta. Okay? So that was the big question. There must be a force, and the force must displace the object. But also, just to take you back to something that's very elementary that we would have discussed way back, probably at primary, when you say energy is the capacity to do work. That statement, if we can unpack it, there's a lot of scientific meaning behind it to say that for work to be done on an object, energy has to be expended or it has to be transformed from one form to the other. Energy of that particular object. So without energy, work cannot be done. So work is energy and energy is work. Why? Because energy, we also measure energy in joules, while work is also measured in joules. So the amount of energy transformation equals to the amount of work that's done on that particular object. So the long and short of it is that we're trying to say that work cannot be done without energy being transferred. Why transfer of energy? Because we know energy cannot be created or destroyed, but what happens to it? It is transformed from one form to the other. Okay, so the big question as to when is work done, beyond just the mathematical analysis of it to say there must be a constant force F and the object must be displaced, there are also energy implications. Hence the topic is work energy. Okay, those two cannot be separated. Right. Okay, now in as far as the quantities, so the uppercase or capital letter W is the symbol for work done by force on an object. To be precise, it's not just work, it's work done by a force on an object, because we want to appreciate the fact that what does work on the object is a constant force F. Right. So the SI unit is the joule. So a joule of work done is equivalent to a force of a joule of a force of 1 Newton displacing an object over a displacement of 1 meter. So in other words, a joule is equivalent to 1 Newton meter. Okay, so if this force F does a joule of work on an object, it means it would have displaced the object for a displacement of 1 meter in the direction of the force. For now, we can carelessly put it that way, right? So 1 joule, in other words, is equivalent to a Newton meter, right? Okay, then the formula sheet is something that I would have alluded to in our opening remarks to say if a problem is a routine calculation, it will carry 3 marks. These are straightforward calculations that each and every one of us must be able to grab the most, number of marks. So you identify the correct formula. Now, if you check, it's W is equals to F delta X cos theta. That's the formula. Let's say you're calculating work done by a force on an object. So it's a simple calculation, formula, substitution, answer. Okay. By now, we are familiar with the kinetic energy in terms of, the type of energy that an object would possess as a result of its motion. So the faster it moves, the greater the magnitude of kinetic energy. We'll remember that from grade 10. So there's nothing new there. Okay. The same goes for gravitational potential energy, which is U or EP. Okay. This is the energy that the object has as a result of its position relative to the surface of the earth. Okay, hence we call it the gravitational because it's within a gravitational field. So these are some of the formulae in the data sheet that one needs to, familiarize themselves with. Okay, you shouldn't see it for the first time in the exam. Try and get used to it, understand it better, know which formula to use under what circumstances. Right. Okay. Now let's look at the foundational knowledge, things that we ought to know. If not, then think of it as a session whereby we remind each other of what is important. Okay. Now, by now we appreciate that work is done on an object by a force. Okay. So the key quantity is the force because it is the very same quantity that actually does work on the object. Okay. Now, where else have we spoken about forces? We've spoken about forces in grade 10 with respect to vector quantities. Very key thing about forces, which will be very important in work, energy and power, is the fact that it is a vector quantity. Okay. Now we are also able to draw free body diagrams, okay, which show the forces acting on an object. Okay. Now, it's a free body diagram. It means, in other words, this body, this diagram is free of the body. So in that case, we represent the object using a dot. Okay. Take note of the common mistakes. There must be a dot. All the tails of the forces that come from that dot must actually make contact with the dot. And there must be also direction. And remember, usually these are not your scale drawings, so we don't take the length of the tail into account in terms of it representing, the magnitude of the force. But it's important to use the acceptable levels, okay, levels of forces. Say, for argument's sake, we talk about Fg, okay? This is the force of gravity or the gravitational force, or a small letter W, okay? So the small letter W represents weight. Weight is the same as the force exerted by the center of the earth on the object towards the center of the earth, which is why it always acts downwards. So take note of the notation that is acceptable in labeling forces in a free body diagram. Very, very important. Okay. Now, what else do we know when it comes to forces? They form the basis of our Newton's laws. All our Newton's laws are about forces. Come to think of it. The first and the second law have to do with an object or a single object in space. Okay, that's why it says a body. How many bodies are there? One. Okay, if a net force acts on an object, if we're saying on an object, we're talking about a single object. Okay, now the first law talks about an object maintaining its position at rest or moving at constant velocity. Okay, in both cases, the object experiences a zero net force. Okay, if there is a zero net force acting on the object, does it mean there are no forces acting on the object? Definitely not. So we are able to use the free body diagram to identify these forces that actually act on the object, right? And then the second law talks about an object that accelerates as a result of a non-zero net force acting on the object. Okay, you'll see how this comes in. Now, for us to say the object would accelerate, we are able to, in a given scenario, to determine the number of forces, their magnitude, and the resultant or the total, which is the net. So the word net means sum, it means total. Okay, let's remember that. So these laws are very critical in terms of understanding work done by a force, because these laws are about, they are essentially about forces, right? So that's how this all comes together. Okay, now that we appreciate that a force does work on an object, or rather work is done by a constant force on an object. Now, there are forces that do positive work, okay? You'd wonder to say, why are we saying positive now? Because we said work is a scalar quantity. But remember, these two quantities whose product give us the work done on that object are actually vectors, okay? So some of the forces, they do work in the direction of displacement. Now, if you look at the cos theta, we've just highlighted it and gave it a different color just to emphasize. Now, if for an object, let's say positive work is done on it, then what does that mean? It means that the angle between the force doing work, okay, let's call that force F, okay, I'll label it F in that direction. And then also we've got the displacement of the object, which is delta X. Let's say it's on a horizontal plane. So you'd realize that the force F that displaces the object for a displacement of delta X actually does so in the direction of the force. So the angle between these two vectors is actually 0 degrees. So if you say cosine from the formula of determining work, if you say cosine of 0, it will give you a positive 1. That positive 1 suggests that the force F in this case does positive work on the object. Straightforward, okay? And then let's look at from the other end, when negative work is done on an object by a constant force F. What does that imply? Let's say, for argument's sake, we've got an object that is displaced in that direction, okay? That's the direction of displacement. And then let's say the object moves to the right while the force acting on the object acts in the opposite direction. I want to use the word opposite, not different, okay? Because even if they're perpendicular, they're not necessarily opposite, but they are different, okay? So it's on a single plane. Now, force F in this case acts in the opposite direction of displacement. So the 180 degrees that we talk of is from angles at a point on a straight line. I think from your mathematics, you'd recall that is those are supplementary angles. So if those two vectors act in the opposite direction, then this object, what is done on it is actually negative work. So that -1 suggests that negative work is done on the object. So the long and short of it, in terms of negative work, is that the force doing work on the object, actually the object is displaced in the opposite direction. Then for that reason, that force F does negative work on the object. Great. Now, we've managed to look at positive and negative. Are there cases where, say for argument's sake, is work not done at all? Yes, there are. Okay. Look at a scenario whereby an object, a force acts on an object on a let's say on a vertical plane, okay, and then the displacement of the object is in that plane, right? Let's say that's our displacement, delta X. Let's say this is a lifting force. Let's call it F for now, okay? Now, this could be a classical example. You are holding a load of bricks or books. You are walking on a horizontal plane. Now, the force that you apply on the books is vertically upwards, okay? While the displacement of the load is horizontal. So those two are actually perpendicular. That's the correct geometrical term, okay? To say that those two are perpendicular. Now, the angle between the two vectors is actually 90 degrees. So cosine of 90 gives us 0. Now, in this case, scientifically, force F, yes, it acts on the object, but it doesn't do any work on the object. Why? Because it acts perpendicular to the displacement. So the reasoning or the thinking as to why certain forces do not do work on the object is precisely because those forces, they act perpendicular to the displacement of the object, which, in a nutshell, it says to us, look, when does a force do work on the object? If it displaces the object in a direction that is parallel to that of the force. Okay, parallel, it means it could be in the same direction of the force or in the opposite, but on the same plane. That's where we have our 0 and 90 degrees, right? Okay, so these are practical examples of positive work, negative work, and no work done on the object, right? So typically the questions that have to do with your reasoning on why a particular force doesn't, do work on the object, it has to do with those two vectors acting perpendicular to each other. And the other thing that I want to remind you, grade 12s, of is that this angle theta, very, very important, okay? Literally, W is equals to F, okay, cos theta delta X, right? Now, theta is the angle between the two vectors, F and delta X, okay? So I've put cos theta in between them just to remind you that theta is the angle between those two vectors and literally is between F and delta X. So don't confuse it when it comes to inclined, okay? Think of it in terms of our special angles. So our special angles in terms of work done now, it's number one, 0 degrees, which is for positive work. Both the force and the displacement are in the same direction. It's 180 degrees, which suggests that the force and the displacement are on the same plane, yet they act in opposite direction, okay? And then the last one, which is no work done. It means the two vectors need to be at 90 degrees or perpendicular to each other, okay? Right. I hope that makes sense, right? Now, when calculating work done on an object by a force, let's go over it once again. We cannot ignore that what does work on an object is a force, okay? And how do we identify forces acting on an object? We draw a correct free body diagram. So if the free body diagram correctly identifies the forces, we are subsequently in a position to identify forces that actually do positive, that actually do negative work, and those ultimately that do no work at all, okay? So and remember, the mark allocation, say for argument's sake, the free body diagram is a mark allocation of 4 marks, okay? What does that mean for us? To us, it says that there are essentially 4 forces. So it's a mark for every correctly labeled and identified force in the free body diagram. So these are easy marks, right? Now the data sheet, very, very important. Draw your attention to the data sheet, okay? Remember, theta in the formula of work is the angle between the force, the constant force acting on the object, as well as the displacement, okay? Now, the SI units, it's very, very, very important, okay? Right, and then moving forward, network or work net, some of you'd want to refer to it as such, right? This is the total work done on an object, and the key word is sum, okay? So if we identify all forces that do work and get the total of all the work that is done by these forces, we get the total work, which is the work net, right? And equivalently, this is the most interesting part, is that we appreciate that what does work on an object is a constant force, okay, that causes the object to be displaced. Now, if we talk about work net, it means what does work net on an object is the net force, right? So work done by net force is the work net, or the net work, whichever way you choose to actually refer to it, okay? Right. So that's very important when it comes to that. But then remember, if we talk about the net force, because work is done by a force, then the type of work done by the net force is the work net. Clear on that? Now, as far as the work energy theorem, by now we all appreciate the fact that work is energy and energy is work, and work can't be done without energy. Okay, after asking the big question in terms of, when is work done on an object, we said to ourselves that, look, work will be done on an object if energy is transformed from one form to the other, but energy of the what? Energy of the object concerned, right? So when we talk about change in kinetic energy, which is our delta EK, what are we saying? We've got final minus initial. That's the change in kinetic energy. And remember, EK, which is K, in most cases, that's how you'd represent it, is equals to half K mass velocity squared, right? So the work energy theorem says that the total work done on an object by net force, because what does total work is the F net. So it says the total work done on an object is equal, right, to the change in kinetic energy of the object. So the greater the change in kinetic energy of the object, the greater the total work done on it. Okay, very, very important. And then, so let's interrogate the work energy theorem and try to understand exactly what it's all about. Okay, now the question that I would want us to guide our thinking is, what causes the object's kinetic energy to change? Why am I so interested in the change in kinetic energy? Because the theorem in its own right says to us that the total work done on an object by net force equals to the change in kinetic energy of the object, right? So the change in kinetic energy is a result of this net force that acts on an object. But now let's review what the Newton's second law says to us. Okay, the Newton's second law of motion states that when a non-zero net force, or when a net force acts on an object, by the way, what happens to that object? Okay, the object accelerates. Okay, so we want to appreciate that the acceleration of the object is a consequence or a result of this non-zero net force acting on the object. Now, if an object accelerates, let's recognize the fact that its velocity will change. Once the velocity changes, the kinetic energy of the object also changes. So in other words, I would want to carelessly think about, the work energy theorem in terms of, Newton's second law, because that's essentially what it is, right? So the acceleration, which is equivalent to the change in kinetic energy, is a result of a non-zero net force acting on the object. And remember, the non-zero net force is the one that does the total work. So the greater the net force acting on the object, the greater the work net, or the total any work that is done on that object, which is also equivalent to the change in kinetic energy, right? Okay, now, so if we can think of it in terms of the fact that the net force that we talk about does the total work on the object, okay? And if the very same net force acts on the object and the object accelerates, there will be an equivalent change in kinetic energy. So in other words, the work done by the net force is equals to the change in kinetic energy, because this work done by net force is our work net, okay? Because what does the total work is the total force. So the total force in this case becomes the net force, right? So it's very important to understand it from this perspective. Okay, now, having had that discussion, I hope your questions are coming through, your contributions, so that we can keep track of whether we are making progress, and if there are some gray areas, we can try and iron them out or polish those ones. Okay, multiple choice, 20 marks. Okay, 20 marks, you cannot obtain 20 marks in less than 20-30 minutes. Okay, so you need to allocate a decent amount of time in responding to multiple choice, right? Because it's a technique on its own. Sometimes it's direct, questions such as remembering, but very few calculations, because they are essentially about your conceptual understanding, how well you understand the physics, right? Now it says here, an object moves in a straight line on a rough horizontal surface. Okay, now the word rough has been written in uppercase, capital letters. What does that tell us? What are the implications of that statement? It says to us that there is a a kinetic frictional force that acts on the object. Okay, kinetic, because it is in motion, so it cannot be static. Okay, let's think about that. Now it says if the net work done on the object is 0. Okay, so this takes us back to our mind map that we once spoke about earlier on, to say that, you know, the Newton's laws are very, very instrumental when it comes to work, because what does work is a force, and the Newton's laws, they capture, you know, a lot of implications about what forces do when they act on objects, right? Now, if there is the net work done is 0, okay, remember, what does the work net is the net force, because we say W net is equals to F net. Okay, so the net force does the work net multiplied by delta X, okay, cosine of theta. That's what we know by now. Okay, now if the total work is 0 newtons, okay, it's 0 newtons, then it means also the net force is 0. Okay, this is 0 joules rather. Remember, this is in joules. All right. Okay, so it means there will be a 0 net force that acts on the object to give us a 0 joule total work, right? But does that mean there are no forces? Definitely not. And there is that principle, or that law, or the law of inertia, that talks about a 0 net force. What happens to an object when there's a 0 net force that acts on it, which is the Newton's first law. It says to us the object will stay at rest or maintain its position, or rather it will move at a constant velocity, right? Now, if we check here, the object is moving. Can the kinetic energy be 0? Definitely not. So we'll eliminate this one. Okay, the change in kinetic energy will be 0, because the kinetic energy will be constant. It won't change, because there's a 0 net force that acts on the object. So it's essentially about Newton's first law. Now it says the object moves at a constant speed. Okay, there is some truth in that. Okay, and then let's look at the other options before we make a rash decision. It says the object moves with a constant acceleration. Wait a minute. What causes the object to accelerate? It's a non-zero net force. So in this case, there's a 0 net force. The object will not accelerate. It will either remain at rest or move at a constant velocity. But now, Bertov, be very, very careful when it comes to this one. Both constant velocity and constant acceleration are uniform motion. But which type of uniform motion has to do with the 0 net force? It's the constant velocity, wherein the acceleration is 0. I hope it makes sense. Okay, there is no frictional force, but we have appreciated that the surface is rough. So this can't be true. Excuse me. Okay, so this leaves us with option B, which is our correct answer. So a lot of thinking and reasoning had to be applied for us to arrive at the correct answer. Okay, I hope it makes sense. Right, and then we've got another multiple choice question here that talks about energy. Remember, work is energy and energy is work. So there is you cannot divorce the two. Okay, whenever work is done, there is energy transformation or conversion from one form to the other. Right. All right. And then it says here, an applied force F accelerates. Okay, I'll underline the word accelerates an object of mass m. Okay, on a horizontal frictionless. This is a smooth surface. I'll underline frictionless from a velocity of v to double v, which is 2v. Now, the moment the object accelerates, what does that tell us about the magnitude of the net force? Is it 0 or non-zero? It takes us back to Newton's second law. In this case, then the object will actually accelerate because there is a non-zero net force. Okay, now the net work done on the object is equal to, all right, there's a theorem that talks about work and energy, and we call it the work energy theorem. If we draw attention to the data sheet, is W net, okay, is equals to delta EK. All right, so W net is equals to EK final, okay, minus EK initial. All right. So EK final in this case becomes half m double V. We are squaring double V. That's the catch. Minus half m v squared. Remember, the velocity changed from v to 2v. So if you do your calculations there, you'd realize that it leaves you with 4 over 2m v squared. Okay, the 4 comes from the 2 squared. Okay, minus half m v squared, right? So 4 over 2 is actually 2 m v squared less half m v squared. Okay, so if you go to your calculator and say 2 minus half, you'll get 1.5. 1.5 in this case is 3 over 2. We're grouping like terms here, mv squared. Okay, so this goes directly to option C. So the change in kinetic energy is from V to double V. So if we apply the work energy theorem, it gives us option C as the correct answer. All right. Okay. Now, long problems are specifically, typically staggered from your easy, straightforward definitions, routine calculations, and then more demanding, like your thinking problems where you have to do multi-step calculations. But here's one perfect example of a straightforward, a scenario of problems where we want to understand that we start by appreciating that forces do work, and in doing so, we must be able to draw the correct free body diagrams. It says here, a skier of mass 70 kg is ready to ski. Okay, started from rest. I'll highlight the word rest there, which says that the initial velocity at point A is equals to 0 meters per second, right? And then the incline is at a slope of 30 degrees to the horizontal as it is shown, right? Okay, and then he skied straight from point A to B over a distance of 120 meters. So this 120 meters distance is our displacement down the incline. So our delta x, if we may refer to it, is equals to 120 meters down the slope or down the incline. Okay, we are told that this ski doesn't poles, they don't touch the snow, so there is no extra force on the gentleman there as he moves down that slope. Okay, so this is not a scale drawing, so we're not going to take measurements from it, right? Now we're told that the total kinetic friction is 150 newtons. So Fk is given is equals to 150 newtons, right? So remember, the frictional force always opposes motion, or it always acts in the opposite direction of motion. Okay, and then draw a free body diagram showing all the forces acting on the skier while he was moving down the slope. So it's a free body diagram, right? It's a free body diagram. So we'll start with the dot there, okay, to show that it's a free body diagram. So this is the diagram that's free of the body. So in place, instead of drawing the whole picture of the man skiing down the slope, we just represent it with a dot. Okay, we appreciate that there is a kinetic frictional force. So if this gentleman is moving downwards, so the opposite direction of motion would be up the slope. So that's our kinetic friction, right? Okay, what else? There is the weight again. Okay, you'd want Fg, right? And then there are 3 forces here. Why are there 3 forces? Because the mark allocation says 3 marks. So for every correctly labeled a force or vector, you'll get a mark for that. Okay, and then again, because the skier is on a surface, so there is a force exerted by the slope or the surface on the man, which is the normal force. Okay, so that gives us our 3 forces. Okay, so it's Fg, normal, and the kinetic friction. Why does the kinetic frictional force act up the slope? It is because that force always acts in the opposite direction of the motion, and it is exerted by the surface. While the skier is on the surface, we also want to appreciate that there is the force exerted by the surface on the skier perpendicular to the surface, which is not necessarily upwards, is the case with most common mistakes that are actually made by learners. So you need to take note also and pay attention to the fact that the 3 marks suggest that there are 3 forces. Having said that, we'll take a short breather for now, for the next 5 minutes, then we'll come back and take the discussion further. See you after the break. Welcome back, grade 12, to our physical sciences session. We're still discussing work, energy, and power. And be kindly reminded that our WhatsApp number for our discussion for today is 064 748 8913. So you're more than welcome to post clarity seeking questions, comments, that form part of today's discussion. And be reminded that you can only text, it doesn't allow us to share video clips or voice notes. So it's just purely for text messaging. Right. So we're still talking about a scenario which involves, work that is done on an object. Right. And we're able now to identify all the forces with respect to the free body diagram. Right. Now let's move on further. It says here, calculate the net work done on this gear as he moves from point A to point B. So that's 5 marks. Okay. So if it's 5 marks, what does it tell us? Is it a routine calculation, simple formula substitution and answer? Definitely not, because this is a multi-step type of a question. We need also to pay careful attention to the mark allocation. Right. So having said that, we have identified the forces that act on the object. Now, the next step is to also identify forces that actually do work on the object. Okay, we've identified the kinetic frictional force. Okay, so the kinetic frictional force acts in that plane. Okay, what else do we have? We've got the normal force that acts perpendicular to the surface, right? Okay, what else do we have? I can think of the weight of the object in terms of the components, because the displacement of the object is along the incline. So that component of gravity is Fg parallel, right? While that component of gravity is Fg perpendicular, right? So if we want the total work, we need to identify the actual forces that do work on the object. So in this case, we've got weight, component of weight, as well as the kinetic frictional force. So total work done, which is the work net, in this case, will be work done by Fg parallel plus work done by kinetic friction, right? But then how do we calculate Fg parallel? Remember, Fg parallel, this formula is not on the data sheet. It's going to be mg sine theta. Now, this gives us the magnitude of the component of weight acting on that object. So in this case, we are told, if we can quickly go back, we're told that the combined mass is 70 kgs, right? So if it's 70 kgs, what are we saying here? We are saying that the magnitude of Fg parallel in this case is going to be 70. Okay, if you go to your calculator, multiplied by 9.8, okay, sine of 30 degrees, right? This gives us 343 newtons. Okay, so our Fg parallel is 343 newtons, right? So work done by Fg parallel is going to be 343 newtons. Okay, what's the displacement of the object? If we can quickly go back, it's 120 meters, right? So if that's the displacement of the object, so that's the constant magnitude of Fg parallel. Now, this is cosine of 0 degrees. Now, cosine of 0 degrees, why are we saying cosine of 0 degrees? Because we know that the Fg parallel acts in that direction, okay, while the displacement is also in that direction. So the angle between them is 0 degrees. So what we're essentially saying is that Fg parallel essentially does positive work on the object, okay? Plus, we're given the magnitude of kinetic friction, which is 150 newtons, right? So this is going to be 150 multiplied by the displacement, which is 120 meters, cosine of what? 180 degrees. Why is it 180 degrees? We appreciate that in this case, the displacement is down the incline while kinetic friction is up the incline, okay? then the angle between them is 180 degrees, right? So the sum of those two becomes 343 multiplied by 120, okay, which is 41160. 41160 plus, okay, and then it's 150 multiplied by 120 times cos 180, which is -1, okay. This gives us a negative 18,000, okay, negative 18,000, okay. Now what that simply means, the negative suggests that that kinetic frictional force does negative work. And in reality, the kinetic frictional force always does negative work. Why? Because it always acts in the opposite direction of motion or the displacement. Okay, so if we add 41160, okay, to that, we'll get positive 23160. 23160 joules. So this is the work net, okay. In other words, we can also think of work net as work done by the net force. Now, if we agree here, we have got these two forces, okay, kinetic friction force, which is 150 newtons, okay, while this one is 343 newtons, okay. This is the magnitude of FG parallel. So if we are to determine the work net, because we know that work net is equals to F net, okay, delta X, okay, cos theta. Okay, what do we have here? We have got 343 plus minus 150. Why minus 150? Because those two, they act in the opposite direction. So if down the slope, the direction of FG parallel is positive, then the direction of FK is negative. Okay, this gives us 193. Okay, so if we say 193, okay, 193 multiplied by delta X, which is 120 cos 0. Okay, why cos 0? Because the net force is in the direction of FG parallel, which is down the incline. So this, what does that give us? We have 193 multiplied by 120 cos 0 is 2316. Same thing, okay, 2316 joules, which is exactly that total work. So what's so special about this example is that it actually allows us to determine total work done on an object using two methods. By calculating the total work, how do we do that? We identify all the forces that do work on the object and get the total of those. Okay, in this case is the component of gravity down the incline as well as the kinetic frictional force, which is acting up the incline. So the total work done by those two forces is 2160 joules, while at the same time we have an option of determining the net force along the incline, which is that 193, which is the sum of FG parallel as well as the kinetic friction. It also gives us the same magnitude. I hope it makes sense, right? Okay, then the most interesting one, guys, is that at the same time, we are able in these long questions to also test our remembering skills, okay, which is the definition. And when it comes to definition, what is our point of reference? What is acceptable by the examiner in as far as the definitions are concerned will be your examination guidelines. Remember, it's all or nothing. Secondly, you must capture the keywords, right? And those keywords must be used in the correct context for you to earn the 2 marks, right? So if you go to your data sheet, which says W net is equals to delta EK, it simply says the total work done on an object by net force equals, okay, there is an equal sign, to the change in kinetic energy of the object. So if you struggle to remember, you can draw attention to the data sheet and put that mathematical equation in words, because that's what it captures, that the total work is the net work, right, done on an object. But what does the total work is the net force, as we have seen in the previous example or in the previous calculation. Okay, so that is equal to the change in kinetic energy final kinetic energy less the initial kinetic energy. That gives us our change, right? But also remember, if the object moves at a constant velocity, there's a zero net force, there'll be zero work net, there'll be zero kinetic energy change. So it speaks to each other. Okay, there's no discord whatsoever. And then if an object is acted upon by a non-zero net force, what happens to that object? It accelerates, either move faster and faster or slower and slower. In both cases, there is a change in kinetic energy, right? Okay, now, and then 5.4 says, determine the magnitude of velocity of the skier at the bottom of the slope. That is 4 marks, right? Now, the moment the question says state the work energy theorem, okay, the follow-up question that has to do with the calculation has to do with the application of that work energy theorem. So for us to apply the work energy theorem correctly, we also need to remember and understand it correctly. Okay, now we want to determine how fast. Okay, but we have the total work, okay, from the previous example. We know that work net, okay, is equals to delta EK. Okay, but what is delta EK? It's EK final less EK initial. That's our change in kinetic energy. Okay, but already we know the magnitude of the change in kinetic energy, or the total work, which is 23160. Okay, so this is 23160. Okay, now let's break it down. Let's break down the change in kinetic energy. It's half, the mass is 70, right? Okay, we also know that the final kinetic energy is something that we're looking for. Okay, but remember, it's going to be Vf squared less 0. Okay, why am I saying 0? Okay, so this is 23160. Okay, if we can quickly go back to the scenario, it starts from rest at position A. So in that 120 meters down the slope, what actually happened is that the skier started from rest, and we captured that the initial velocity is 0. So while the initial velocity is 0, the EK initial is also equals to 0 joules. I hope it makes sense. All right. So the substitution of the 0 is very, very important. It's a necessary, it's a requirement. Okay. Now we are left with this mathematical problem. Otherwise, all the science is done here. We are going to just isolate VF. Okay. So for us to get VF, we have to multiply 23160 by 2. Okay. Multiply by 2, it gives us whatever that is, and then divide it by 70. Okay. And then after that, we'll determine the square root. Right. Okay. So if we determine the square root, it gives us a VF of 25,72, okay, meters per second. Right. So what's the important thing here is that we used the work energy theorem to determine how fast the skier will be moving right at the bottom of the slope, because we know that it started from rest, and we have been able to determine the magnitude of the total work done by those forces as it moves that displacement of 120 meters down the slope. So it's more of a mathematical problem once you understand how you have to actually isolate the final velocity there. That's the speed at the bottom of the slope, but it says here magnitude of velocity, so the direction is not important in this case. I hope this example makes sense in terms of determining total work and using the work energy theorem to determine whatever it could be. Okay, it could be kinetic energy, it could be speed, it could be the mass, it can be anything. All right. Okay, and then moving along, grade 12, we have a scenario here again that talks to energy, because we are so much into kinetic energy, which is the motion that relates to your work energy theorem. The statement says the kinetic energy of a car moving at constant speed v is EK. All right. So in other words, EK is equals to half m v squared. Okay. Now, I want you to listen to this argument, closely, right? So half mv squared is ek. Okay. What is on the left-hand side equals what is on the right-hand side. So this term, half mv squared, represents ek. Are we happy? Right. Now it says the speed changes to half v. Now, did the speed increase, decrease, or remain the same? Because what we know by now is that the kinetic energy has to do with the amount of energy that an object possesses as a result of its motion. So the faster it moves, the higher the kinetic energy. The slower it moves, the lower the kinetic energy. Now, what has happened here is that the change in kinetic energy is from V to half V. So that's a decrease in kinetic energy. So what do we expect? Do we expect the kinetic energy when we have halved the speed? Do we expect it to increase, decrease, or remain the same? You know those questions. So that's where we begin to eliminate. Now, if we decrease the speed, we expect kinetic energy to also decrease. So two options are totally out for this reason, okay? Option C says double Ek. Then option D says 4 times the initial kinetic energy. Okay, now both C and D, what's common with them is that in both cases, kinetic energy has increased, which is not true because what has actually happened here, we have decreased the speed. We expect the kinetic energy to also decrease, while option C and D tell us an opposite story. Okay, now let's see with half the speed what's going to happen. So we know that the new kinetic energy is going to be half same mass. Okay, what's the new speed now? It's v over 2 squared. So we're squaring half the speed, not having the square of the speed. So that's a mathematical problem there. Okay, so where does that leave us? Okay, this leaves us with half m v squared multiplied by 1 over 4. Okay, but what did we say is half mv squared? Half mv squared is ek. Okay, ek multiplied by 1 over 4. Okay, which is the same as 1 over 4 multiplied by ek, which leaves us with option A. Right, so that's the thinking that one has to apply when it comes to these mathematical relationships. Your understanding is very, very important. So we don't just shoot in the dark. We read the question, the problem statement with an intention to understand. Then after that, we can go through the steps of eliminating so that we enhance our chances of getting the correct answer. Right. Okay, having said that, graphical interpretation, very, very important. We cannot underestimate the importance of graphs because it's a cross-curricular skill, something that we have obtained from our maths. We also need to apply it in the physics. It says here, a car moves from rest, or underline rest, okay, in a straight line under the influence of a constant net force. So there's a constant net force, right? Which one of the following graphs best describes the net work done on the car in relation to its displacement? Right. Okay, this is basic elementary conceptual understanding of what work is all about, because we know that W is equals to F delta X cos theta, right? So there is a constant force that acts on the object, okay? Now, if there is a constant force, right? So F is constant, we realize that W is directly proportional to the displacement. What that simply says to us is that the further the constant force F acts on the object, the greater the amount of work is done, okay? So more displacement equates to greater magnitude of work done. So these two are directly proportional from the equation there. So obviously, we can't be having a greater displacement for the same amount of work. That's why option C is out. Then there's this exponential relationship between work and displacement. We didn't square anything on the right-hand side. So option A becomes wrong. And D doesn't exist because, look, the greater the displacement, the lesser the work. Then for a certain maximum displacement, there is actually there's actually zero work done on it. So then that's a problem, okay? Because the mathematical equation says work is directly proportional to the displacement provided the force remains constant. So option B captures that relationship. Then when are the two quantities directly proportional? Very, very important is that if you draw a graph of those two quantities, one against the other, you obtain a straight line that passes through the origin, or a linear graph that passes through the origin. So option B captures that quite correctly with our understanding of work. Right. Now let's talk about conservative forces. Now we understand that what does work on an object is a force, right? Now, if we talk of conservative forces, we're actually, or a conservative force for that matter, we're actually talking about the work, the force for which the work done in moving that object between any 2 points is independent. So the key word is independent of the path that is taken, okay? So if you drop an object, it could be experiencing free fall, right? What actually happens is that there is the gravitational force that acts on that object, okay? So if you calculate the amount of work done, okay, between those 2 points, it doesn't matter whether it moves on an incline downwards or upwards. The change in gravitational potential energy has to do with the gravitational field. So that's why we think of the weight of the object as a practical example of what we refer to as a conservative force. So if the force is conservative, in most cases, if that's the force that acts on the object, the total mechanical energy of that object remains constant. And remember, energy is work and work is energy. So we cannot talk about work without referring to the energy, right? But then on the contrary, if we talk about a non-conservative force, that's supposed to be a non-conservative force, is the force for which the work done in moving the object between 2 points is dependent on the path. Now, friction or kinetic frictional force is a practical example of a non-conservative force. And when a non-conservative force acts on an object, that is usually, it's not a closed system. So even the total mechanical energy of that object does not remain constant or is not conserved. So I want you to think of it in terms of that, in as far as the non-conservative. Okay, so the key word here is non-conservative, right? Okay, let's understand the link, because we can't talk work without referring to energy, because these are one and two in the same concept. So there are 3 energy principles that are essential for us at this stage. The first one is the principle of conservation of mechanical energy, right? From grade 10. What do we know about this principle? What does it tell us? It tells us that in a closed system, the total mechanical energy of an object remains constant. Okay, so if it's a system which is there are no non-conservative forces, or there are conservative forces only, it simply says to us that the total mechanical energy will remain constant. So this is for an isolated system. Okay, it is for an isolated system. All right. While the work energy theorem works for both closed and open system, whether they are both conservative and non-conservative forces, when there is a net force that acts on the object, that object, according to Newton's second law, it will accelerate. While it accelerates, then it will bring about a change in kinetic energy. At the same time, if the object is moving at a constant velocity, while doing so, there are both conservative and non-conservative forces, and the object moves at a constant velocity. We know there's a zero net force acting on the object. So it takes us back to the Newton first law. So this is for both closed and open system, where you have got conservative as well as non-conservative forces. Yet the work done by a non-conservative force, this is the interesting part. While there are non-conservative forces, work is done, to oppose, to overcome friction. So we can carelessly think of it in terms of work is done due to friction. So while there is frictional force, it's no longer a closed or an isolated system. So we expect that the total mechanical energy will change. So that change in total mechanical energy is equal to the work done by that non-conservative force. In most cases, it will be the frictional force as a classical example that we have mentioned. Now, let's look at practical examples of these conservative and non-conservative, and under what scenarios or context will these, questions of understanding of conservative and non-conservative forces be examined. Okay, it says here, during an accident, a driver applies brakes to bring the car to rest. So ultimately the car stops. Okay, right? So while the car is slowing down, then the big question is the car accelerating? Definitely, it is accelerating. So we mustn't think of acceleration in terms of faster and faster, because at the same time, while the object moves slower and slower, there is a change in velocity. So in both cases, there is a non-zero net force. So while the driver applies brakes to try and bring the car to a complete halt, what actually happens is that the car accelerates in the opposite direction of motion, which is in the direction of friction, which is the net force in that case. So which is true again for the Newton second law, right? So the combined mass of the driver is given as 800 kilograms, right? And then the investigators at the accident scene measure the length of the car skid marks on the level road. So that displacement or that change of position from the moment the brakes were applied until it stopped completely is 88 meters, right? We are given the coefficient of kinetic friction, which is 0.42, right? And then take note, the coefficient of friction does not have a unit, because the coefficient is actually the ratio between the frictional force and the normal force. Okay. So this is going to be Fk over normal. Okay. And remember, this ratio, the kinetic frictional force is measured in newtons, while the normal force is also measured in newtons. That's why it's a ratio, hence it doesn't carry any units. Okay. Now the forces acting on the car while it's braking are given as, or shown as, x, y, and z in the above illustration. Okay, identify a name. So this is another way of accessing or checking whether you can draw a free body diagram. Now you have been given a free body diagram. You are asked to identify correctly the forces involved. They've been given letters x, y, and z. Okay, the force y. What is force y? Before we identify force y, we need to be able to describe it correctly. Remember, every force is an applied force. Okay, it's always exerted by something on an object, or it's always acting on an object by something, right? So if you look at force y is exerted by the surface on the car perpendicular to the surface, and that description fits exactly the normal force. Okay, so that's where it all begins. Okay, if you can correctly describe the force, then you can correctly identify it as well, right? So that's one mark. No explanation, nothing fancy, simple and straightforward. Okay, so this is the grade 11 work on free body diagrams, force diagrams, vector diagrams that we referred to earlier in our discussion, right? Here it says, which one of the above forces is a conservative force? It's one mark there. Okay, now we must choose from x, y, and z. Okay, what is a conservative force? It is the force for which the work done in moving an object between those 2 points is independent of the path taken. And there's only one force there, which is a classical example of a conservative force, which is the weight. So the weight in this case is identified by force x. So if you say x, it's fine. Okay, they didn't say identify x. If you say x, it's still acceptable. So x, in other words, is the force of gravity or the weight, small letter w, because uppercase W stands for work done by force on an object. Okay, now 5.3 says what, okay, I want to underline the word what, is the magnitude of the force work done by force y. Okay, now we have correctly identified force y as the normal force. Okay, it acts perpendicular to the surface. Now this object moves on that plane to our right. That's our displacement. And then this is our normal force, which is force what? Force y. Okay, What do we know about a force that acts perpendicular to the displacement of the object? We know that that force does not do any work. So the question says what? I often say, these action verbs are very important. If it says determine or calculate, it will give you a minimum of 3 marks in most cases. But if it says what, it's like, what is your name? You answer directly. It's either you know or you don't. So in this case, the question says, what is the magnitude of the work done by force Y? The big question is, does force Y do any work on the object? If not, why? Yes, most certainly that will be 0 joules. Okay, work is measured in joule. So if you say 0, it could be 0 at kgs, it could be anything. So 0 joules is the magnitude. So the magnitude must have a unit for you to get the correct answer. So in this case, it's going to be 0 joules because force Y acts perpendicular to the displacement of the object. Okay, and then which one of the above forces does negative work on the car? Okay, so force Y does not do any work, okay, because it acts perpendicular to the displacement of the object. But then if we talk about negative work, what do we know? It's a force that acts in the opposite direction of the displacement of the object. So this is the displacement of the car while the driver applies brakes, and then this is our force Z. This force acts in the opposite direction of displacement. It's 180 degrees. So force Z is actually our kinetic friction, okay, which acts in the opposite direction. So in this case, force Z does negative work on the object. Right. I hope that makes sense. Okay. Different scenario again. We've got a car of mass 700 kg that moves up a RAF. Okay. RAF would have been in some cases written in capital letters just to draw your attention to the implications of that or the science behind it. Okay. So the angle of the incline is 30 degrees to the horizontal. Okay. What, again, this looks familiar to us now. And remember, each time the question says what, usually it's 1 or 2 marks. Okay. No need to calculate. Think about your understanding of the concept because that's what the question actually demands of you, right? It says, what is the net work done on the car if the car moves up the incline at a constant velocity? Okay. If the object moves at a constant velocity, there is a 0 net force acting on the object. And we know that work net, okay, is done by F net because what does work on an object is a force. Okay. This is what we know by now. So if there is a 0 net force, okay, there will be a 0 what? Total work done. So 0 joules due to 0 Newton net force acting on the object. But does it mean there are no forces doing work? Yes, there are forces doing work, but the total of the work done by all these forces that act on the car gives us a total of 0. Okay, that's what it means. Okay, and then it says here, draw a labeled free body diagram showing all the forces that act on the car as it moves up the incline. Now, what is important here is to also pay careful attention to the mark allocation. Remember, the mark allocation tells us the number of forces that act on the object. Okay, so there are 4 marks there. Okay, here is our car. It's a free body diagram. The diagram is free of the body. Okay, so we've got this force that takes the car up the incline, which is the force of the engine on the car. You can call it the applied force, even though every force is an applied force. Okay, we would accept that. Okay, what else? We've got the weight of the car, which is vertically downwards. So that's our FG. So what is actually happening? The Earth, center of the Earth, exerts a force towards itself on the car. So that's why we are saying that the car is drawn downwards towards the center of the Earth. That's the weight. Okay, and then this is a rough surface. If the car moves up the incline, the kinetic frictional force acts down the incline. So that's our kinetic frictional force because it always opposes the motion. Then while the car is on a horizontal on a surface which is inclined, there is a force exerted by the surface on the car perpendicular to the surface, which is a normal force. So those are the 4 forces that act on the car while it moves up the rough incline. So the word rough is the one that gives us the fact, the sense that there is a constant kinetic frictional force acting on the car, right? Okay, that was straightforward. Now, the car starts from rest at the base, okay? It starts from rest at the base of the slope and accelerates. Okay, I'm going to underline that. What causes the car to accelerate? Remember, Newton's second law says to us that when a non-zero net force acts on an object, the object will accelerate. So while there is acceleration of the car, it's an indication that there is a non-zero net force that acts on the car. So it's very important to recognize that. Okay, now the car's engine exerts a force of 6,000 newtons. Then we've got a coefficient of kinetic friction of 0.32, right? So that's the rough surface. Okay, we've encountered this before. I think by now, when it comes to long questions that have got to do with work and energy, you can almost predict or anticipate or expect that you'll be asked a question on define or state the work energy theorem. Okay, this is becoming a lot more like a pattern. So it says to us it's very essential that we go back and remind yourself what the work energy theorem actually says. And remember, we've also noticed a pattern that when the question says state the work energy theorem, the follow-up or the subsequent question would have to do, in most cases, with the application of of the work energy theorem and other related ideas, right? So it says use the energy principles, okay, of which the work energy theorem is one of them. Okay, use the energy principles to calculate the magnitude of the velocity of the car after moving a distance of 70 meters up the incline. Okay, the car is accelerating. So there are quite a number of things here that we have to take into account. Without getting into the details, let's identify those forces. We've got this applied force of 6,000 newtons. Okay, that's our 6,000 Newton force. Okay, in terms of the forces that actually do work. Okay, what else do we have? We have the kinetic frictional force. Okay, we have the kinetic frictional force. What else do we have? We have got Fg parallel. So these are the forces that act parallel to the incline. Over and above, we've got Fg perpendicular, okay, which doesn't do any work because it's perpendicular to the displacement. We also have the what? The normal force, right? So this is the other version of our free body diagram. But then the question wants us to find how fast it moves. So this has to do with the work energy theorem. Now we have to determine the amount of work that the applied force does, okay? Because we are saying work net is equals to delta EK, okay? That's where it all begins. Then total work is work done by the applied force, okay, plus work done by kinetic friction, plus work done by Fg parallel, right? This is equals to change in kinetic energy, which is actually Ek final less Ek initial. All right. So the whole science is centered around this equation, which has to do with the work energy theorem, right? Now, because we are able to determine, the work done by the applied force, because we're given the magnitude of the applied force, but we have a task to determine Fg parallel, okay, which is Fg parallel is equals to mg sine theta. Okay, remember grade 12, this equation for determining Fg parallel and Fg perpendicular is not provided in the data sheet. You need to remember from your trig ratios, okay? So if Fg parallel is mg sine theta, meaning Fg perpendicular becomes mg cos theta, right? Now, if we can calculate the work done by Fg parallel, in this case, are we given the mass of the car? Yes, it's 700 kgs, okay? So we can calculate work done by Fg parallel, okay, which is equals to Fg parallel, which is mg sine theta, which is 700 multiplied by 9.8, which is mg, and then sine theta. Theta is the angle of the incline. Take note, do not confuse this to the angle between FG parallel and the displacement. Okay, so this is sine 30 degrees. Okay, that's our FG parallel. The displacement we are told is 70 meters. Yes, it's 70 meters. Okay, now there's something special about FG parallel in this case. It acts in the opposite direction of displacement. So the angle between FG parallel and displacement is 180 degrees. So it does negative work. So how much work is done by FG parallel? It's going to be 700 multiplied by 9.8 sine 30, right? Multiplied by 70, okay? Multiplied by negative 1. Negative 1 comes from cos of 180, okay? So it's going to be 700 multiplied by 9.8, okay, sine 30, okay. That gives us 3430. We multiply that by the displacement, which is 70, okay, all right, which is 24. So work done by FG parallel is negative, very important, that negative 240, okay, 100 joules, okay. And then what about the work done by kinetic friction? Okay, we have to find kinetic friction. We know that F kinetic is equals to mu k multiplied by the normal force. But remember, the normal force in this case is it's equal in magnitude to Fg perpendicular, right? Because they are equal in magnitude and opposite direction, because they are action-reaction forces in this case on the car. All right, so we can say then it's going to be mu k, all right, multiplied by mg cos theta. Okay, so that is the magnitude of the normal force, which is equal to that of FG parallel. This is another formula again that is not provided in the data sheet, right? So if we are to determine the work done by kinetic friction, where does that take us? It will be WFK is equals to kinetic friction. The magnitude of kinetic friction is in itself is 0.32, which is the coefficient, multiplied by the mass. The mass in this case is 700, okay, multiplied by cosine of 30, okay, cosine of 30, okay, that's 193. So if we multiply that by 70, which is the displacement, okay, obviously with -1, so this work done by that is negative 135, okay, 79,28 joules. Okay, remember, always it must be in 2 decimal places. But then it's easy for us to determine work done by F applied, which is going to be F applied, okay, delta X cos 0 degrees. Okay, this is straightforward. Why are we saying so? Because the applied force by the engine on the car is in the direction of the displacement. So it's a multi-step question. It's going to be that 6,000 multiplied by 70 multiplied by positive 1. So this gives us a value of 420, okay, 1,000 joules. Okay, so now we have the 3 values of work done by applied force, work done by kinetic friction, and work done by FG parallel. So if we equate that to the change in kinetic energy, we are able to determine the value of V, which becomes the only unknown. Now, because of time constraints, you really understand that this is a multi-step question. That's why the total number of marks is 8. It looks scary, but look, it's doable as long as you understand how you identify the forces, how you carry out the calculations, and then also take into account the direction, right? Beyond these are one of the few examples that we thought we can use for the purpose of today's discussion. But because of time constraints, I think it's also very incumbent on you to say, try and expose yourself to as many scenarios as you possibly can. Try and practice as much as you can. From myself, Themba Ncube, because of time constraints, we shall call it a day for now. All the best. Goodbye.